All right, I'm going to teach you inverse tangent integrals, but I also want to compare them to just logs so we can talk about the differences between them. And then even eventually, I guess really we should put on here versus partial fractions. You probably haven't learned about partial fractions yet, but you can, and you will eventually. And a partial fraction integral would look something like maybe x squared minus 1 dx. All three of these are really similar. They all have a quadratic in the denominator, but they are going to be drastically different integral techniques, and there's reasons. Okay, inverse tangent. Inverse tangent, if you think about what is inverse tangent rule, inverse tangent is going to be the rule, the standard basic rule is going to be du over u squared plus 1. That integral is inverse tangent of u. Okay? Then you have a log rule. Log rules are going to be the integral of du over u. We know that. The integral of du over u is just the natural log of u. And then partial fractions, that's going to be later on, and that's going to be a technique where we take 4x squared minus 1 and we write it as like a over x minus 1 plus b over x plus 1, and we find a and b, and then we integrate the result. Again, hold off on that, but I just want to compare it because they're all very similar in how they look. X squared plus 1 in the denominator, x squared plus 1, x squared minus 1. Again, partial fractions will be in your future, but eventually on the test, you'll have to distinguish between all three. Let's just focus on these two right now. Logarithm is going to be a du over u. So you see how this is a quadratic and this is a linear function. So they work well in terms of a logarithm, typically, that you can get a du over a u with a little chain rule. Again, this integral, we would love that to be a 2. The integral of this, well, it would just end up being, again, with a little u substitution, the natural log, 2 times the natural log of x squared plus 2 plus c is this integral. This integral is the 4. Well, that can just come out, and we just integrate, and we get 4 inverse tangent of x plus c. Again, inverse tangent is when you have a constant. Again, that can come out, and you get some easy du over x squared plus 1. So eventually we want to really recognize these. Okay, I am going to walk you through, though. You guys don't like this one at all. You know it's inverse tangent, and somehow, some way, you end up getting the coefficient wrong of what happens if this is, we'll say 3 over x squared plus 4 dx. Again, that plus 4, you guys hate it. You really want it to be a plus 1. Look at this standard rule. It's got to be a plus 1. Something squared plus 1, and that, that u and then du. If this is a 4, it just makes you guys upset. You really struggle with handling that because you have to make that a 1. Well, how do you make that a 1? Well, there is only one way. You factor. Again, it's going to be an inverse tangent because it's a constant over x squared plus something. Again, it's not like there's no x's. It's quadratic plus something. That means it's an inverse tangent rule. What you have to do, first of all, I can get this 3 and I can pull that out in front. Okay? And what you have to do is you have to make that a plus 1. So then you factor a 4. You can factor a 4 from this. So look at this and factor a 4 from it. Okay? What happens if you factor a 4 from an x squared? And again, you don't do that much. You don't ever take a 4 from something that doesn't have a 4, but it turns out it's easy. You just leave a 1/4 plus 1. Think about that. Again, if you redistributed this, meaning if you multiplied this 4 back into the denominator, 4 1/4 would give you x squared. 4 times 1 would give you 4. Right? We can factor a 4, take 4 from 4, and take a 4 from a 1, and you leave a 1/4. Okay? So we're getting closer. We now have it. So we have the plus 1. But now I need something squared. I can't have 1/4 times x squared. The rule is something squared. And so what we do is we take 1/4 x squared and write it as x over 2 squared plus 1. And look, I'm getting really close. I have u squared plus 1. Okay, and now I do my u substitution. Well, u is x over 2, which means du is 1/2 dx which implies that dx is actually 2 du. Come over here, 3/4 integral dx is 2 du. X over 2 is my u squared plus 1. That 2 can come out, so that's 6/4. 6/4 is 3/2, and then I just integrate du over u squared plus 1, but that's the standard integral, inverse tangent of u, and u is x over 2 plus c, and I'm done. Again, this 4 causes all sorts of problems, but it's really not that bad. There's just 2 steps. Step number 1, you have to make it into the standard rule, right? This is the standard rule for inverse tangent. You have to make it a plus 1. That's the key. So whatever this number is, if it's a 4, and again, it usually is a square. It's 4, 9, 16, 25, something like that, but it doesn't have to be. You have to factor it out. So take this 4 and factor it from the denominator. Leave a 1/4 and leave a 1. You can always check, multiply that 4 back in and make sure you got the original. And then you can't have something times x squared plus 1. It has to be u squared. So you got to make this into something squared. So 1/4 x squared is the same thing as x over 2 squared, right? If you square this, you get x squared over 4, which is the same thing. But now you have something squared plus 1. There's your u. So then do u substitution. If u is x over 2, then du is 1/2 dx. Substitute, and all of a sudden, boom, you got the standard rule right here. The integral of du over u squared plus 1 is inverse tangent of u, and this 2 times 3 over 4. Those factors will always eventually just give you some number out in front. Okay? I'm going to do one more, kind of walk you through it again, so you get at least see it twice. It's not going to be anything new. I'm not going to say anything different. I'm going to do the exact same thing. I'll just use different numbers. Okay? Let's make this a 5, and we'll make this an x squared plus 9. And again, I'm going to do the exact same thing. I'm going to notice that it is an inverse tangent. It's something squared plus a number, and there's no x up here. If there was an x up here, it'd be a logarithm rule, but it's not. It's an inverse tangent. And again, I know I need it to look like this, because once I make it look like this, then I know the integral is inverse tangent of u. Okay, first step, factor out a 9. And I'm going to go ahead and move out the 5. Why not? So I'm going to take a 9 from the denominator. Right? This dx is the only thing left in the numerator. All right, if I take a 9, I factor a 9 from an x squared, I have to leave a 1/9. I take a 9 from a 9, I get a 1, right? I'm factoring a 9 from the denominator. Feel free to multiply it back in and check to make sure you got this back. I know I need to fit this form. So if it's going to be that form, I know then I have to write it as something squared. It's got to be the integral of some du, right now it's just dx, of something squared plus 1. Well, 1/9 x squared is x over 3 squared plus 1. When I'm getting close, now I have it to u squared plus 1. So u must be x over 3, which makes du 1/3 dx, which tells us that dx is 3 du 5/9 integral, and instead of dx, right, 3 du over u squared plus 1. This is 15/9, which is the same thing as what, 5/3? And then the integral of du over u squared plus 1 is inverse tangent of u, which is x over 3 plus c. And again, hopefully you can start to see some patterns and being able to do that quicker. But again, this is one that first you have to recognize as inverse tangent. And third, you have to be able to deal with the u substitution, the fact that this isn't a 1 and it's a 9. And that 9 ends up just creating that factor of 3. Again, hopefully on the last one, this was a 4 and this was a 2. If this was a 16, you'd get a 4 there. You can try to start to see those patterns. But eventually on the test, not only is inverse tangent a problem that you get this factor right, but again, the big thing is eventually you start to recognize the differences between this is an inverse tangent integral, this is just a logarithm integral, and then this one is actually a partial fractions method, which we'll learn probably in a couple days. Okay?